this T is a mapping from U to V, and dimension of U is M, and dimension of V is N. First vector space that I will define is called K, which is called kernel of T. That is defined as set of vectors U in V in U such that T of U is equal to 0. That means all those vectors that are mapped to zero vector in V, null vector in V, is called the kernel. This becomes a vector space. You can easily verify all the rules of and also this kernel of T is a subspace of which vector space? It is a subspace of which vector space? U or V? Kernel, because I am taking elements in U, so it has to be a subspace of U. Correct? So this is a subspace of U. Now, so I remember, even though I told you just now that I don't ask whether you have done the homework or not, yesterday I told you that prove that S is a subspace if and only if it satisfies closure under addition and scalar multiplication. Have you done that? Did you write the proof? You have tried that. Okay. So anyway, let us look at the proof. Maybe the tutorials after the T. But let me say that it can be proved. Okay. So you have to just check closure under additivity and scalar multiplication. That's a vector addition and scalar. So you can take U1 and U2 that are in this, such that T of U1 is 0, T of U2 is 0. But T is a linear transformation, correct? And U1 plus U2, if you take T of U1 plus U2 is equal to T of U1 plus T of U2, that also will be 0. So U1 plus U2 also is in K. So you can write the proof very easily, addition, closure under addition and scalar multiplication. So it becomes a subspace of U. This is the first vector space that you can define. Once this is pertinent to a given linear transformation. And the second vector space that you can define is what is called range of U. Which is equal to set of all vectors V in V such that V is equal to P of U for some U in V. That means all those elements of V which have a pre-image in U. Ask those elements of V which have a pre-image in U. This is the subspace of V. Is a subspace of V.
We have not defined T from V to U.
T?
You are just saying T of U.
T of U. Yeah.
T of U is defined from V to U.
No. T of U is V. U to V only, right? So I am putting U in U. T of U is equal to V. This is called range of T. This is also a subspace, which is second vector space that we get. Third vector subspace that we can define is, I will call it as ER, that is span of row vectors. That means each row you consider as a vector and then take the span of those row vectors. This also, you know, span is always a vector space. I don't have to talk about verifying whether it's a vector space or not. But now tell me, it is a subspace to which vector space? Span of row is a subspace to subspace of
dual space of
no, I have U and V, only two vector spaces. So this should be a subspace of one of these two vector spaces. Why U plus V? How many rows are there? How many rows are there in the T matrix? N rows. So what is the maximum dimension of span of n rows? N rows means n vectors, right? Span of n vectors will have n dimension, provided if all the rows are, if all the vectors are linearly independent. So maximum is n, but it can be less than n also. If some rows are, all the rows are not linearly independent, then the dimension will be less. So this will be a subspace of V. V is n dimension. Correct? And fourth one is span of column vectors. So row vectors of T. Span of column vectors of T. There are n columns. So maximum dimension of vector space is equal to m. If all the columns are linearly independent, then you have vector space as m. Otherwise, it will be less than m. So this is, so it is a subspace of U. So every given linear transformation, you can define these four vector spaces corresponding to every given linear transformation. Okay, so as some of you promised that you will attend some future courses, I will use all these things when I do group theory in the month of May. If I have every theorem that I prove, I will have to use all these results. I will construct vector spaces and then talk about these kind of specific vector spaces of linear transformation, to prove some results, and then do some applications of this linear transformation. So these are the four vector spaces that you can define. So these are these four vector spaces can be defined any this kernel is also called a null space of T. Null space of T. That means T takes all these vectors of this space to 0. So Kernel is also called null space. Some textbooks use this word called null space. Now let us look at this example that we have just talked about. In this case, P is equal to 1, 1, 1 minus 1, 1, 2. What is the kernel of T? I want to construct these 4 vector spaces for this problem.